So the comparison will take place on two data sets. At this time, I have mentioned to you the data one is the small data. Okay, we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, we have 8 data. And then the second data set is a list of salary of the population in Seoul. So there are 8 million people. So it means there are 8 million data. If I use the data one, if the runtime is log n, then the running time performance is log 8. Do you still remember log 8? What does it mean by log 8? So I give the hint here. If it is log base 2, and then I want to make the logarithmic of 8, then the answer will be 3. Okay. Because we know that this log means we want to know the exponent. What is the exponent? So that the 2 power of some values equals to 8. And we can just refer to this log 2 8 equals to x. Okay. It means if we have this one log base 264, then it means we have 2 power of x that equals to 64. So what is x? In this case, we have the x equals to 6. Okay. So if we have the log base 2 8, then it means the running time will be 3. Okay. So if we have 8 million data, then the running time will be log 8 million. If the runtime performance of our algorithm is n, then when we use the data one, the running time will be 8. Maybe if it is in second, we have 8 seconds. If we use the data 2, then the running time will be 8 million seconds. Okay, so that's why we need to understand the growth rate. Because if we know the running time, we can analyze. If we use the data 1, how big is the performance? And if we use the data 2, how big is the performance? So for example, this one. We have 2 algorithms. This is for sorting algorithm. The first algorithm is insertion sort. The other algorithm is merge sort. Let's say you already run your experiment. This is number of elements or number of your data. And after you run this, you will have the runtime performance, and the runtime performance in microseconds. So the red is showing like this, and the blue is showing like this. So which one is better? The blue or the red algorithm? Yeah. Blue. Why blue algorithm? The blue algorithm, it shows good performance at the first time. But when the data is getting lots, the running time is getting very high. But what about the red color? It shows very high performance time at the first time, but when the data is getting high, the data is getting large, it shows better than the blue one. So in this case, it is better to choose the red color. Okay. If you do with the runtime performance analysis like this one, yeah, it is easy to check. Okay. But later on, you need to also find the complexity. The complexity means what is the n, whether this is the n power of 2 or it is 2n log n. So when you have this complexity, you can compare with the experiment result. In this case, the experiment of the insertion sort with 1 million items, it takes 70 hours. With 1 million items, the merge sorts, it took 40 seconds. Okay. So which one will you choose? First, we will use the merge sort. It is better for the time performance. And also for this one, n log n is better than n power of 2. Okay, so you learned last time about the function. Okay. The n log n is still better than the n power of 2. So if you use maybe, yeah, I use my computer, which is very slow, then it's 70 hours. Now the computer is getting good and the computer is getting better and better in terms of the performance. So if you run in the high GPU computer, maybe it will be faster. Okay, it is faster. Maybe when you use the high performance GPU with the insertion sort, you can run 40 minutes. But with the merge sort, you can run maybe 0.5 seconds. Okay. So it still shows that this one is much better because it is faster, regardless the computer specification. Whenever we do this kind of complexity analysis, you need to understand the constant factors. What is the constant factor? We call this is a constant factor or the lower order terms because it will not affect to the complexity. For example, if we have this one, it is linear function. Why? Linear function always have only n. Okay. So if I have like 2000 multiplied by n plus 5152, what is the function? This is still linear function because we have only n. Okay. This we call as quadratic function. Why? You have the n power of 2. So this is the highest. We got the lower order terms. The lower order term is the n. We can exclude this one for the complexity analysis. So for example, if it is the linear, okay, if it is linear like this one, so if you have a function like this, it might be something like this one because there's a constant at the first time, and then it will go on the same line at the end. Okay. The same with this one, quadratic function. In the quadratic function, maybe when you have no constant, it will show like this one. If you have any constant, maybe it's stuck here, but the growth rate will have the same line. Okay? The growth will be the same at the end. It regardless how big is the constant and how big is the lower order terms. And it's also applied to the space complexity. The space complexity means it is to estimate the memory requirement for the execution. It means, for example, how many data for the input, how many space you need for the input, how many space you need for the intermediate process. So if, for example, you do with the deep learning, so in the deep learning you have the input, and then you have a process, and then you have an output. So how many data that you need to save in this intermediate process? And then how many temporary data in the data structures? So if you create any kind of matrix, okay, so it means you need to have some storage. And the required space of the output. So how big is the space for the output? We call this is the space complexity. For example, if we have this kind of problem, what about the space complexity? If we look at the input, this will be the input. And we want to run the function squares. So the input, we have 4. When we run the squares, we go to the first statement. The first statement, square numbers is empty. So we will put the numbers, when numbers in n means this parameter. So number in n is 2. So the square numbers, append, it means we want to add. Okay. Number multiplied by number. It means 2 multiplied by 2, which is 4. We want to add it into the square number. And then we go to the next number, which is 3. Again, we will append 3 multiplied by 3. And then we go to the next 5. Again, we will append. So at the end, we will have 4, 9, 25, and 64. So how many space do we need? In this case, we have only n numbers. If we have the input n, the output also will be n. Then we have just n. It requires memory allocation for the numbers of items in the input list. So say the number of elements in the input is n. So the space requires increase with the input size. So if I have 10 numbers, then we need to save also this into 10 numbers. So it depends on the numbers, because this is the space complexity is n. The first part, it was about the algorithm analysis, and we need to understand the big O notation. So the big O notation is a kind of function. Given a function fn and gn, we say that Fn is O is the big O notation of Gn, if there are positive constants of C and N0 such that we have the following condition. So Fn should be less than or equal to the C is the constant. Here the condition is positive constant, not negative constant. So we have the C as the positive constant multiplied by Gn. And this is for all n that is greater than or equal to N0. Again, N0 should be a positive constant. Now, for example, I have this example. 2n plus 10 is On. How can I say this 2n plus 10 is On? First, I would like to say that this is the Fn. And then I will use this one as the Gn. So the Gn means I would like to know whether the 2n plus 10 is On, is n. Then there will be a function 2n plus 10 is less than or equal to the C multiplied by Gn. C is a constant and Gn is n. In this case, it is n. So you can apply the basic mathematics for this one. So 10 is less than equal to Cn minus 2n. And then we can put C minus 2 multiplied by n is greater than equal to 10. And then I have the n is greater than or equal to the 10 divided by C minus 2. Okay. Now for this one, we have the condition if there are positive constant C and N0. So if the n is greater than 10 divided by C minus 2. So you can pick any number. Is there any positive constant for C so that it is a positive? Let's say I choose 3. So 3 minus 2, then it will be 1. So if it is 10 divided by 1, then this n, we call this is N0, it will be 10. And we can specify the N0. We can specify N0. If it is 10, then okay. Then there will be a positive constant. Because we have 10 positive constant when we put the C equals to 3. What about this one? The function n power of 2 is not On. N power of 2, okay, in the left part, we want to check whether it is less than or equal to the constant multiplied by n. Because On, the function is n. So if we want to apply the mathematic rules, so we have the n power of 2 less than equal to Cn. So we will check. So n is less than a constant. So the above inequality cannot be satisfied since C must be a constant. Because we have a constant and this one, it will be not a constant. So it will not be satisfied. when we look into the big O examples, this is the background idea how to get the big O. We have 7n minus 2. So we want to check whether it is n or not. Or we want to specify what is the big O. For the first, I want to check whether 7n minus 2 is on or not. The same idea with the previous mathematical formula, we can have the 7n minus 2 less than Cn. And then you can derive this formula. So at the end, you will have the C and N0. We should have a positive constant, a positive number. So if you look at this formula, later on you need to have the C equals to 7, and then you will have N0 equals to 1. Then the condition is true. So 7n minus 2 is 1. If I want to check the 3n power of 3 plus 20n power of 2 plus 5, whether it is on power of 3, the same with the previous formula, I can check this one, 3n power of 3 plus 20n power of 2 plus 5, it is less than or equal to the Cn power of 3. And then when you derive this formula, you can check that there will be a constant C equals to 4 and the N0 is 21. What about the 3 log n plus 5? The same idea with the previous one. We can look at the formula 3 log n plus 5. It is less than or equal to the C log n. And when you do the derivation, you can get the C equals to 8 and N0 equals to 2. So for all this one, it is true. So we call the big O rules. Now the big O rules, the same with the constant factors that we learned before. If Fn a polynomial degree D, polynomial degree, it means if you have like n power of 3, n power of 2, n, and then plus constant. So it is the polynomial. So Fn is OND. D is the degree. It can be 3, it can be 2, it can be 1. So if you have this kind of polynomial, first drop the lower order. Lower order means if it is n power of 3, n power of 2, n power of 1, and c, so you can drop this one. Drop means you can just remove. And drop the constant factor. So you can drop the constant factor. And also, if we have like this one, 30 n power of 3 plus 5 n power of 2 plus 30 n plus 5,000. Oops. 30 power n power of 3 and maybe 25 n power of 2 plus maybe 3,000 n plus 550, for example. So the idea is drop the lower order terms. Drop the lower order terms, then we will drop n power of 2, we will drop 3,000 n, and then drop the constant factors. drop the constant factor, we drop this one and drop the constant in this case. So we can say that with the big O rules, this big O will be O n power of 3. We can use the smallest possible class of function. 2n, we call it, this is On. Instead of 2n is On power of 2. So this is not correct. We can use the simplest expression of the class. If 3n plus 5, it is On. Instead of 3n plus 5 is O3n. So the 3 is not meaningful. We can just create the O n for this one. So that's why I think you have questions. Some of you have questions about the previous section. Like this one. You still remember this example? So some of you ask, professors, why you don't put here the line number 7? Actually, whether you put this or whether you not calculate this one, it doesn't care. Because at the end, we know that it is constant. Okay. If we do this one, we do care only the AND operation. One operation, we don't care. Because it is constant. So at the end, we just need to consider the higher order terms, which is the n, which is only linear. Okay. So whenever you do like this operation, maybe which one is correct? It is 3n plus 3 or 3n plus 4. It doesn't matter. Because at the end, for the big O rule, it will show just, okay. What I mentioned here is to show you how we can get the higher order terms. Because if you don't show the step by step like this one, you will miss this one. Whether this is n or there might be some problems with this n power of 2. So the important thing is you need to find the operation, whether it is constant or n power of 2 or n power of 3 and so on. That's what we call as the asymptotic algorithm analysis. So the asymptotic analysis of an algorithm determines the running time in big O notation. To perform the asymptotic analysis, we find the worst case number of primitive operations executed as a function of the input size. So you do the operation like one operation, and then next is 2 operation. Okay, this is okay. But when you have n operation, and then you have n multiplied by n operation, so we want to find the worst case. The worst case is the n multiplied by n, so it is the worst. And we will express this function as the big O notation. The big O notation means you do not care the constant. You just care the higher order terms. So at the end, you will find the big O. It is the O power n power of 2 for this kind of O. So for example, if we want to say the minimum max, the find max, okay? So the one that I showed you before, the find max algorithm, this one. If you look at this algorithm, if you do one by one, this two operation, this is two operation, this is two AND operation, this is two AND operation, this is 0 until n operation, this is one operation. So we just care the higher or the worst case. In this case, the worst case is until n times. Then we can say that this is the O n. So since the constant factor and the lower order terms are eventually dropped anyhow, we can disregard them when counting primitive operations. Okay. So that's the meaning by the big O notation or the asymptotic algorithm analysis. I think I will explain this one on Wednesday. Okay.